push record here and get started, okay? All right, so we did mention spectroscopy a little bit with respect to Chapter 5. So what type of spectroscopy were we using in Chapter 5? There was some rotation of something.
Direction.
Something, a wave, right?
Yeah.
Right, so what is this called? We have a chiral molecule, right? We shoot in plane polarized light. What does it do to that plane polarized light? A chiral molecule. It will rotate that plane polarized light. What is that? What did we call that? That study of shooting in light, plane polarized, rotation. What do we call that? No, it's called polarimetry, right?
Oh.
So the first type of spectroscopy that we introduce you guys to in organic chemistry is polarimetry, right? And again, polarimetry deals with chiral molecules. Chiral molecules rotate plane polarized light depending on the type of chirality center that you're looking at, okay? All right, so now we're going to kind of continue on that because we did review a couple of concepts with respect to light when we went through polarimetry, okay? So number one, what is light?
Either
Waves and particles, like lots of little things coming to mind. Specifically, it's radiation. What type of radiation? It is electromagnetic radiation, okay? So in electromagnetic radiation, what we have is oscillating electric and magnetic fields, right? So electromagnetic radiation has both an electric field component, right? It also has a magnetic field component, and both of these fields are oscillating, okay? They are also, most importantly, perpendicular to each other, all right? And they're doing this oscillation, they're doing this perpendicularity, and they're propagating in the direction of wherever we're shining light at, okay? Okay, so there was also brought up at this, when I just asked about what light is, this idea behind this particle wave duality of light, right? So the first way that we imagine light, or we try to model light, is as a wave, right? So if we were to draw a wave, there are a couple of characteristic features with respect to waves, right? So one way that we can characterize a wave is via what is called the wavelength, right? So wavelength is going to be defined as the distance between, let's say, a crest and a crest, a trough and a trough, or a node and a node, right? It's essentially the distance that a full wave covers, okay? So how do we represent wavelength in terms of chemistry? What Greek letter do we like to use for wavelength? It is this guy, which is gamma, right? No, God, Chelsea. Yeah, wait, oh no.
No, I got it wrong.
No, it's gamma. No, it's not gamma, it's lambda. Why am I, okay. Lambda. I'm gonna have to re-record this. I know. Lambda really makes me worried about my brain. Okay, so lambda, that's how we represent wavelength. This again is wave length. And then if it's a length, then how do we usually measure it? What unit do we use to measure it? Just basic unit of length is meters, right? So with respect to wavelengths, we're usually measuring in some prefix multiplier of a meter, right? Because we're measuring a length here. Okay, so that's one way that we can characterize a wave, if we are imagining light as a wave. Another way that we can characterize it is via its frequency. So what is the difference between wavelength and what is a frequency?
How many times?
Yeah, so frequency is how many times. For waves, it's specifically how many times a full wave will pass a particular point in a given period of time. So how many full waves get through a point in a particular period of time. Frequency, we represent as the Greek letter nu, right? So this is our frequency. And how do we measure frequency? It is how many cycles occur per unit time. So how do we usually measure something like that? It's not going to be like a distance. It's a per time, right? So 1 over time. What is our usual unit of time? Seconds, right? So for frequency, it is a 1 over second. We can also write inverse seconds. What is this unit also called? 1 over second is you'll maybe remember, it's also called a hertz, right? So it's unit of frequency. Okay, so we're imagining light as a wave, right? We know that we can characterize it via its wavelength as well as its frequency, okay? And wavelength and frequency are actually related to one another, right? And they're related to one another via the speed of that wave, right? If we're dealing with light, what is the speed of our wave? What is the speed of light?
Time?
So speed of light is 3 times 10 to the 8th meters per second, right? This is going to be the constant proportionality that relates our wavelength to our frequency, okay? And so particularly, frequency is equal to the speed of light, c, over the wavelength, lambda. And so if you have one, you can have the other, you can calculate the other, because again, light is going to travel at a constant speed, which is 3 times 10 to the 8th meters per second. Okay, so now, just as a review, what is the relationship between frequency and wavelength? Are they directly proportional to one another, or are they inversely proportional? So if we look at frequency and wavelength here, are they directly proportional or inversely proportional? Right, so frequency and wavelength are inversely proportional to one another, meaning that the larger the wavelength, the smaller the frequency, and vice versa. Okay, so this is an inverse proportionality. Okay, so that is if we treat light like a wave, right? But we also know that light has particle-like properties, particularly in how it delivers energy, or the energy of light, okay? So light, with respect to energy, delivers energy in what are called photon or quanta. And these are going to be like these little packets of energy, these little packets of light. So with respect to energy, energy has nothing to do necessarily with the dimness or the brightness of the light that we're shining. It has everything to do with the frequency of light. Okay, so this was the big contribution that Einstein made, was he related energy to frequency, right? And this little guy in the middle, this little h, is just a constant. It's just Planck's constant. It's not important. We're really looking just for the relationship between energy and frequency, okay? So now, given this equation, energy and frequency, are they directly proportional or inversely proportional?
Directly proportional.
So these guys are directly proportional. So there's a direct proportionality. The larger the frequency, the larger the energy, and vice versa. What about energy and wavelength?
It has to be inverse.
So since there was an inverse relationship between frequency and wavelength, there's also an inverse relationship between energy and wavelength. So these guys are inversely proportional. The larger the wavelength, the smaller the energy, and vice versa. Okay, so now that's a brief introduction to light, right? And how we imagine light. We've got wavelength, we've got frequency, and we also have a relationship with energy, okay? So now the question is, what is spectroscopy? What are we doing with respect to spectroscopy, okay? And so the basic idea behind spectroscopy is when you have matter, right? Matter has all different types of atoms, all different types of bonds in it, and you shine light onto matter, there is going to be an interaction, right? So sometimes that matter will absorb light, depending on the bonds it has, depending on the electrons, etc. Sometimes it will not. Okay, that is the entire study of spectroscopy, is the interaction between light and matter and what we can actually garner for how they interact with one another, what we can determine about the actual matter itself via its interaction with light, okay? So this isn't the first time that we've talked about spectroscopy before. Ideally in 151, 152, you guys are also introduced to a basic idea of spectroscopic techniques, right? And you have probably utilized what is called a spectrophotometer before, at least in 152, I know that you have. Right, so if we go back to the idea in 151, 152 of what spectroscopy is, one thing that we did do is we looked at UV visible spectroscopy, right? And as just a reminder, when we talk about, let's say, an atom, right? We know that an atom has specific orbitals, right? what resides in those orbitals, or what are those orbitals representing?
Where the electron?
Electrons, right? So remember that with respect to those orbitals have what is called quantized energies, right? What do I mean by quantized?
Position?
So yeah, the energy of each orbital is very, very, very specific, right? And so what I mean by quantized is that we have these electrons, and they reside in these orbitals, right? But they can't ever reside in between the energies of these orbitals. These orbitals have very specific energy spacings, and electrons can't actually be in between. It can only either be in one or the other. These energy spacings are what I mean by quantized, very specific values, okay? So in UV visible spectroscopy, what we learned in 151, we have an electron. Let's say it's in our ground state orbital, our 1s orbital. And let's say we shine light onto this atom that has this electron in its ground state, and the energy of that light is directly equal to the difference in energy between these two orbitals. What happens? So we have an electron, it's here, it's in its nice little ground state. We shine light, that light has energy that's directly equal to the difference in energy between these two orbitals. What's going to happen to that electron? It'll jump up, right? It'll be promoted into that higher orbital, right? That higher energy orbital state, okay? When that occurs, what do we see? So we get this promotion of this electron. We have shined light on this sample. Let's say that we were plotting the absorbance of light in our sample as a function of wavelength, right? What would we see on a plot like this when we're looking at absorbance, where 0 is no absorbance, and let's say 1 is full absorbance, right? Again, what we're calling this is absorption. We're taking in that energy, we're taking in that wavelength, we're promoting that electron to a higher energy state. Whatever that wavelength is, it's not going to get through into the detector at the other end of our sample, right? So how would we depict this on an absorbance versus wavelength plot where 0 is no absorbance at all and 1 is full absorbance? What do we see in our spectroscope? We see a wave, right? We'll see a peak that correlates to whatever wavelength is associated with this energy, right? So when we shine light into matter, right, and that light has equal energy between the energy spacings between the two orbital levels, we'll see a peak in our little absorption plot due to that absorbance of light. Okay, that is the basic idea behind spectroscopy. When we deal with UV visible, we're looking at electron transitions, right? And so where is UV visible? What is that region on the electromagnetic spectrum? What is the wavelengths for ultraviolet and visible light?
400 to 700.
Right, so this guy, we're dealing in nanometers, right? So nanometers, particularly with respect to UV visible, this ends up being about 900 nanometers to about probably like 350-ish, right? So wavelengths, or light with those particular wavelengths, are going to have enough energy to promote electrons between orbitals. And that's what we're actually looking at with respect to UV visible, okay? So that was the basics, right? We had a nice little absorbance plot, or absorbance spectrum. We're looking at absorbance as a function of wavelength, and this is usually in terms of nanometers. If we get a peak that tells us that at that wavelength, this light had an energy that was directly equal to the energy spacings between the orbitals, and so we got absorbance, right? What was the reverse? What if we had an electron already in a higher energy state, and what if it relaxed back down to the lower energy state? So this guy, instead of staying up here, it was like, hey, I'm okay, I'm gonna relax back down and come back down here. And let's say that it gave off light that had that exact energy spacing. What is that called? It's not absorbance, but when we relax back down and we give off light that has that particular energy spacing, what is that called? We come back down, we give off light. This is called emission. So where do we see emission? things that fluoresce, things that phosphoresce, all of those glow-in-the-dark things, these guys, they're up in an upper energy state, they're relaxing back down to a lower energy state, and they're giving off light that has that equal energy. Okay, so again, that is the basics. That's the basic idea behind spectroscopy, and that's what we have seen already with UV visible spectroscopy. So now, what is the purpose of this chapter? Because it's not going to be ultraviolet visible spectroscopy. Instead, what we're going to be dealing with is IR spectroscopy. Right, so this is where we start our introduction to spectroscopy. When I say IR, what is that telling you about what region of the electromagnetic spectrum we're dealing with? IR, what other regions are there? There's microwave, there's gamma rays, there's infrared, right? So what we're looking at with respect to this region of the electromagnetic spectrum, we're looking at the infrared region in IR spectroscopy, okay? Now, if we go back up to our little electromagnetic spectrum, right, we'll notice here we've got visible light, right, and that's at about, again, 400 to 700 nanometers. Where is infrared relative to visible?
Between 2 and 15.
Is it at a larger wavelength or is it at a smaller wavelength?
Smaller.
So if we're at nanometers here, and we're going out to nanometers, less nanometers, we're at micrometers in the infrared spectrum, so is this at a larger wavelength or smaller wavelength?
Larger wavelength.
Larger wavelength, right? So compared to UV visible, infrared is at a larger wavelength. What is that going to tell you about energy relative to UV visible?
More energy.
Larger wavelength, what is the relationship between energy and wavelength?
It's directly proportional.
Energy and frequency are directly proportional.
Oh, that's right. I'm sorry. It's an inverse proportion.
Right, so in this infrared region, we're looking at a larger wavelength comparatively to visible, and we're also looking at a smaller energy. Okay, so what are we going to learn? What type of interactions or things are going to be occurring at this smaller energy level, right? Because ultraviolet visible gave us electron transitions between orbitals, right? We're not going to be seeing electrons in the infrared region of the electromagnetic spectrum. What are we going to be seeing, though? You probably don't know this, and it's fine, right? But I'm trying to introduce it. So what are we actually going to be looking at this smaller energy, at this larger wavelength? So, just like orbitals are quantized with respect to our various atoms, there are a lot of other things in molecules that are also quantized, okay? And one of the big ones that we talk about with respect to IR spectroscopy is vibrational and rotational frequencies, okay? So number one, if you have two atoms and they're connected by a bond, those bonds can undergo what we call vibration, right? So what do we mean by vibration? Movement, right? And so what we imagine this as number one, we can imagine as like an accordion, right? Where we're vibrating like two masses on a spring. We can also see it as bending, so bonds will bend. What about rotation, right? Because they also have quantized rotational frequencies. What do I mean by rotation?
Opposite positions.
So can bonds rotate?
Yes.
So that's one rotational thing that we can do, right? What else can we do? Rotational motion is not just stuck with bonds, but we can also literally rotate in space, okay? So this vibration, right? So bending, stretching, this rotation, all of these guys have very quantized energies as well, meaning that if you have a bond, it's only going to be able to vibrate at a certain frequency, right? If you want to promote it, it can vibrate at a higher frequency, but that frequency is set, right? And they're going to have set energies, just like our orbitals had set energy spacings, okay? So it's going to be this vibrational frequency and this rotational frequency that we're going to be looking at in IR spectroscopy, okay? And so what's essential for that is that you have molecules that have bonds, because if you don't have bonds, there's not going to be any vibration, there's not going to be any rotation, okay? Okay, so this is the basics behind IR spectroscopy. We're going to be dealing with vibrational frequencies, And we're going to talk about all the various things that are going to go into that, okay? One thing I do need to note is that really the only thing we're going to take away from IR spectroscopy is the type of functional group that is present in a molecule, right? This is going to be very indicative, or these various stretching frequencies are going to be very indicative of functional groups. What do I mean by functional groups?
The ones affected the most about the bond that's affected.
Give me just a common functional group.
CO2.
Remember in Chapter 2, we had all these functional groups we had to learn. Esters,
Oh, yeah.
right? Things like that.
Acids.
Which one was what?
Alcohol.
Alcohol, right? So this is what I mean by functional group. Is there an alcohol present in our molecule, right? Another common functional group, ketone or an aldehyde, right? We call this specifically a carbonyl group. What other things? Alkenes, right? What about this guy? Alkynes. There are a lot of different functional groups. This is what we're going to be learning with respect to IR spectroscopy. What specific functional group is present in our molecule, okay? Now, why is that important? And I probably haven't introduced why spectroscopy is important at all. So let's say that I made a compound, right? And I knew with respect to that compound that it was made up of 2 carbons, it was made up of 6 hydrogens, and an oxygen, right? The whole purpose of spectroscopy and what we're going to be using this for is determining what the structures of these guys are, right? Because if I have this information, okay, I've got 2 carbons, I've got 6 hydrogens, I've got an oxygen, are there a variety of different combinations?
Oh my God, yes.
Yeah, right? So one thing that this could be is an ether, right? This could be a dimethyl ether. What else could this be?
An alcohol.
It could be an alcohol group, right? This could be ethanol, etc., right? So the whole purpose of this is figuring out, we've got this guy, we're trying to figure out what the actual structure is. And that's what IR spectroscopy, as well as NMR, is going to help us obtain. Okay? Okay, I hate this. Okay, so now that's the basics, IR spectroscopy. What else is going to be different, okay, comparatively to what we have learned before? So in an IR spectrum, we're actually going to be kind of looking at the inverse of what we would have expected in a UV visible spectrum, right? So in UV visible, we were looking at absorbance as a function of wavelength, right? And if we had promotion of an electron, we would see what specifically at a given wavelength? We would see a peak, right? Because again, 0 absorbance meant nothing was absorbed, right? And 1 absorbance meant that everything was absorbed. So we were looking for peaks in our absorption spectrum. Absorption spectrum. Now, what happens in IR? So in IR spectrum, it's the complete opposite of that, right? Instead of absorbance, what we're looking at is what is called percent transmittance, right? So when we shoot in light and 100% of it gets transmitted, that means that nothing got absorbed, right? So at 100% transmittance, nothing is being absorbed, right? Whereas at 0% transmittance, everything is being absorbed. So it's essentially the flip of our absorption spectrum, okay? Because of that, instead of peaks, what are we looking for in our IR spectrum? We're looking for troughs, right? So we're looking for things like this. This is what we're looking for overall. That's telling us that light is being absorbed, right? We're looking for troughs instead of peaks. Okay, so that's number 1. Number 2, what else is different? So we were looking over here at wavelength, right? But down here, this thing is called wave number. It's not wavelength, right? Instead, wave number is kind of like a normalized value of frequency, right? So wave number is defined as this guy. And what it is the frequency of light divided by the speed of light. So instead of wavelength, we're actually looking at frequency here. Okay, so just to make that point, with respect to wave number and with respect to frequency, these guys are directly proportional. So again, wave number is kind of a measure of frequency. So because of that, we have 4,000 over here versus 400. which side of the spectrum is going to have the highest energy? Or how does energy relate with respect to the spectrum? Going from 4,000 wave numbers over here to 400 wave numbers over here. So frequency, wave number, directly proportional. How does frequency relate to energy?
That's also directly proportional.
Right, so energy and frequency are also directly proportional. So where is the largest energy on this spectrum? Is it over here on the left,
Yes.
or is it over here on the right?
I would say on the left.
On the left, right? So again, the higher the wave number, the larger the energy. So the larger the wave number, the larger the energy of whatever transition we are looking at. So everything over here on the left hand of the spectrum is going to have a higher energy than everything over here on the right of the spectrum. Okay, all right, so that's the basic idea behind an IR spectrum. Note, looking at it, is it super clear what any of this means?
No.
No, right? So again, we know that we're looking for troughs as opposed to peaks here. We know that energy is high over here for whatever these things are and low over here, but how can we make sense of any of this? Right, so that's what we're going to talk about next, how to make sense of our various peaks in an IR spectrum. So each peak is going to be characterized by three separate things, and we're going to talk about how they are affected. So the first one is the wave number it's at, right? So that essentially is the energy that it's at on our overall spectrum. The second is the intensity, right? So what do I mean by that? So why is this guy so much deeper than something like this, right? That's what I'm implying by intensity. And then the third is the shape. And again, a good example of that is why is this so broad and this guy is so much more narrow? Okay, so each of these peaks is going to have a specific wave number, it's going to have a specific intensity, and it's going to have a specific shape. And each of those things is going to tell us something about the functional groups that are present in the molecule. Okay, so where do we start? We're going to start with wave number, right? So how do we know what type of bonds we're looking at depending on what wave number they're absorbing light at? Okay, and again, higher energy part of the spectrum, lower energy part of the spectrum, okay? Okay, so what we should note is that depending on the bond, depending on the atoms that are attached to the bond, we're going to actually have different energies, and that's going to tell us a lot with respect to where we're going to absorb in the IR spectrum, right? So for example, in a carbon-hydrogen bond, so again, we're looking specifically at the bond and the stretching vibrations of that bond between carbon and hydrogen, we get a very large energy gap. Right, so there's a very large spacing between these vibrational frequencies in this carbon-hydrogen bond. How does that compare to a carbon-oxygen bond? Again, looking at that bond between carbon and oxygen, how does the energy difference between those vibrational frequencies compare to the carbon-hydrogen vibrational frequencies?
CO2 is a smaller gap.
Smaller gap, right? So smaller energy difference. What would that mean in terms of frequency at which we would absorb light for these types of transitions? So larger energy tells us what about the frequency of light at which we would absorb? Larger energy, large gap is going to mean
More frequency.
higher frequency, right? So higher frequency compared to a smaller gap. What does that mean in terms of wave number then? Higher frequency, we're going to absorb at a higher wave number.
Wave number.
Because again, wave number and frequency, they're the same thing.
Yes.
But again, that's what we're actually plotting. We're plotting wave number on our IR spectrum, okay? Okay, so I am telling you that, right? I'm telling you carbon, hydrogen, that bond has a larger energy difference in these vibrational transitions compared to a carbon-oxygen bond. But how would we know that? So the idea behind this and what we're looking at with respect to IR spectroscopy is we're imagining these vibrational frequencies, right? So we're imagining this bond vibrating, okay? One way that we can model that is like two masses attached to a spring, right? So if I have two masses attached to a spring, and I pull back one of the masses and I let it go, what happens? It sits there and it vibrates, right? So the whole idea behind this is that this guy can only vibrate at specific frequencies. It can vibrate like this. If we want to promote it, it's going to vibrate a little bit faster, but it can't vibrate in between that, okay? How should we model that? Do we have any reference to physics to model two masses that are attached via a spring? Yes, with respect to those vibrational frequencies. So the way that we model this vibration and understanding the frequency at which we can vibrate is via kind of a modified version of Hooke's law. So Hooke's law states that the frequency, we're just going to go with the frequency here, of this vibration is equal to a bunch of constants that we don't care about times the square root of what is called the force constant divided by the reduced mass, okay? And again, the way we are modeling this is, here's atom number one. We're going to call that mass number one. We have a spring attached to them, and this is going to atom number two. We'll call this mass number two, okay? So this is going to be our carbon-hydrogen or carbon-oxygen and vice versa, okay? Again, we're looking at the frequency of the spring and how much it vibrates, okay? So we're ignoring this because it's just pointless, right? There's a square root here, but we really don't care about that. How does frequency relate to, number one, this force constant?
It's directly proportional.
Right, so frequency, that's an ugly frequency. Frequency and our force constant are directly proportional to one another, meaning the stronger the force constant, the stiffer that spring, the larger the frequency, okay? What does that mean in terms of a bond, though? Stiff spring versus not stiff spring? So what would that mean in terms of bond strength?
Stiff, hard to break. Not stiff, easier to break.
So our force constant we model as our bond strength, okay? So force constant we model as bond strength. So overall, the stronger the bond, the stiffer that spring, the higher the vibrational frequency. Because again, these force constants and frequencies are directly proportional. Okay, so again, we'll state that again. Bond strength, stronger bond, stiffer the spring, the larger the wave number, larger the frequency. Okay, so then what is the other thing that's going to affect this? So we have ignoring, we have bond strength and the relationship between frequency. What is this guy on bottom? Reduced mass. So we can ignore the actual equation for reduced mass, right? But just note that it's a combination of the masses on the two springs, right? So this is going to be mass one. This would be mass of carbon versus mass of hydrogen, okay? So reduced mass is the combination of them together. So now what is the relationship between frequency and reduced mass?
Inverse.
They're inversely proportional, right? So frequency is inversely proportional to reduced mass. So the smaller the reduced mass, what can you tell me about the frequency?
The larger.
Right, so smaller the reduced mass, the larger the frequency, or larger the wave number we would see this at. So now can you give me a reason why we see such a large energy gap between carbon and hydrogen comparatively to carbon and oxygen? Because of the masses, right? Hydrogen to anything else is going to have one of the highest frequency absorbances or highest frequency transitions because it is the least massive of all of the atoms or all of the elements. So anything attached to a hydrogen is always going to have a very, very, very high frequency because of that.
That means it has a weak spring, right?
Strong spring. It's more of, not, okay, so the strength of the spring or the stiffness of the spring is the force constant. It's the bond strength.
Okay.
The other component is the reduced mass.
I see.
So the less mass doesn't tell us anything about how strong that spring is. It just tells us that we're going to have a high frequency. Okay, so now, how does that translate, right? So how do these various things or various factors, the bond strength as well as the mass of the two atoms on either side of the bond, how are they going to actually affect our overall frequencies at which we see absorbance? So first one we'll talk about is the mass of the atoms. So again, note, as we have a carbon attached to hydrogen versus deuterium versus oxygen versus chlorine, what's happening overall to the combined masses of those two? So as we go from left to right and we combine those masses, we're seeing an increase in mass, right? Because chlorine's super heavy, hydrogen's not heavy. So in going from left to right, we're increasing the combined mass, which is increasing essentially the reduced mass. What's happening overall to the wave number at which we're seeing absorbance? It is going from left to right, we are decreasing, right? So decreasing wave number. So again, the mass and the frequency, mass and the wave number, these guys are inversely proportional. So the larger the combined mass, the smaller the frequency at which we're going to absorb. Okay, and we can see that as we have a hydrogen attached to the same atom versus deuterium versus oxygen, etc. As we increase that mass, we're going to decrease the wave number of absorbance. Okay, so then that is mass. What about strength of bond? So as we go, let's say, looking at bonds between carbon and nitrogen, carbon and nitrogen, carbon and nitrogen. So for all of these guys, mass isn't going to play a factor because it's the same atoms on either side of the bond. What does change for these guys, though?
The frequency.
So specifically, what type of bond do I have here?
A triple bond.
This is a triple bond. What type of bond do I have here?
Double.
It's a double. And this guy is a single. So is this going to be a matter of looking at reduced mass, or is this going to be a matter of looking at force constant or bond strength?
The force constant.
Force constant, right? So who do you think is going to be the strongest or the stiffest spring?
The triple bond.
The triple bond, right? So the stronger the overall bond strength, the stronger the force constant, the higher the wave number of absorbance. So those are the two factors that really play a role in the overall IR spectrum: the masses of the atoms of the bond, as well as the bond strength. Okay, so that's the basic idea behind wave number. What this is going to do, though, is it's actually going to divide up our IR spectrum into two separate regions, right? Those two regions are what we call the diagnostic region, and then the other one is called the fingerprint region. So this guy over here on the left-hand side of the spectrum is diagnostic, whereas this guy is called fingerprint. And how do they differ with respect to one another? So the kind of the dividing line between diagnostic and fingerprint is about 1,500 wave numbers, so inverse centimeters. Everything to the left of that is diagnostic. Everything to the right is fingerprint, okay? Also note what types of bonds we're going to be looking at in each different region. So for the fingerprint region, what type of bonds are we looking at in terms of triple, double, single? All single bonds. So everything down here is essentially just single bonds, right? Whereas as we move to the left of this little dividing line, as we move into the diagnostic region, what type of bonds are we looking at here? Doubles and triples. And then the big one, what type of bonds are from about 2,700 to 4,000? So this is going to be anything attached to a hydrogen, right? Because again, that hydrogen was the lightest element, so it's going to always absorb at a very high region of the IR spectrum because of that. Whereas anything between here and here, we're looking at double and triple bonds. We're looking at bond strength there. Okay, so diagnostic is actually going to tell us functional groups. It's going to give us a lot of information about the functional groups that are present in the molecule. Fingerprint is not really useful for us. It's not going to tell us very much. But I will note that the reason why they call it fingerprint, so every human has a unique fingerprint. Every molecule has a unique fingerprint region spectrum. That's why they call it fingerprint, right? But again, for the most part, when we're using IR spectroscopy, you should ignore everything below 1,500 inverse centimeters. Okay, All right, so we're going to specifically talk about this region and what we can tell about it briefly, and then we'll do a question, okay? But just note, between about 16 and 1850, we're looking at double bonds. And then from about 21 to 23, we're looking at triple bonds, okay? And then everything above 27, we're looking at something attached to a hydrogen. Okay, so now what other little information can we garner from this? If we focus in on that other thing attached to a hydrogen, specifically for things where we have carbon attached to a hydrogen, there's more information that we can actually gather about what type of groups may be present in our molecule, okay? Okay, so let's imagine that we are looking at molecules that have a carbon-hydrogen bond, right? Carbon-hydrogen bond, carbon-hydrogen bond. So both of these guys, for all three of these, we're not looking at any effect with respect to mass because they all have the same mass. As we look at this, we're looking at a carbon-hydrogen single bond, right? We're looking at a carbon-hydrogen single bond. We're looking at a carbon-hydrogen single bond, right? You would imagine, okay, mass, single bond, it's the same thing for all three of them. They should all absorb frequencies about the same region, right? Do they? No. No, right? So for our first one, we're at about 2,900, the second about 31, and the third about 33, okay? So who has a more energetic absorbance? We'll call this guy number 1. This will be number 1. This will be number 2. And this will be number 3. Who absorbs at a higher energy? 3, right? Because specifically 3,300 is a larger frequency, a larger wave number than 29 or 31. Why? Why would that need more energy? Going back to the idea behind the two different things that affect this, mass and then the force constant, the bond strength.
It has a higher force constant.
It must have a higher force constant because the mass is the exact same, but why does it have a higher force constant? Why is this bond stronger than this bond or this bond?
Because the attachment of the C type of bond.
So let's also go back just really briefly to think about bond strength and bond length, right? So the shorter the bond, so shorter bond, what does that do in terms of bond strength? Is it a stronger bond or is it a weaker bond?
It's a weaker bond.
Stronger, right? So the shorter the bond, the closer those electrons get with the other nuclei, the stronger the overall bond, okay? So now, if we consider the carbon that each of these hydrogens is attached to, how do they differ as we go from left to right? Here we have what type of carbon, hybridization-wise?
SP3.
SP3. Here we have SP2. Here we have SP, right? For SP3, what percentage of those orbitals is S character? 25%. So this guy is 25% S character, right? 75% P. What about SP2? How much is it S character? This is 33 S character, and then for SP, how much is it of S character? It's 50, right? So again, who is closer to the nucleus, S or P? S, right? So because this guy is 50% S character, it makes this thing a shorter bond. And so because it's shorter, it's stronger. And so we actually see absorbance at a higher wave number, at a higher energy because of that, because of the fact that it is 50% S character. And we can even distinguish this in an IR spectrum. So if you guys don't believe me that this S character stuff matters, it does, right? For SP hybridized carbon hydrogen bonds, we see it at about 3,300, whereas SP3, we see it about 2,900, less energy. Okay, so how are we going to utilize that? So what I would always suggest is that you look in the region, in the diagnostic region, at about 3,000 inverse centimeters, and you draw a line, okay? If everything is to the right of that line, what does it tell you that you don't have any of? So again, 3,000, if everything is over to the right, then we know that we don't have any sp2 or sp hybridized carbon-hydrogen bonds, right? But if we draw that line and we do get stuff, oh, pardon me, yes, we do get stuff to the left, right, then we know, especially if it's at 31 or if it's at 33, that's telling us that there is an sp2 hybridized carbon-hydrogen bond or an sp hybridized carbon-hydrogen bond.
Wait, what?
Okay, so again, we're trying to figure out what type of functional groups are present in our molecule, okay? One way to use this carbon-hydrogen stuff is to draw a line at 3300. If nothing is to the left of that, then that tells you there is no sp2 hybridized carbon-hydrogen or sp hybridized carbon-hydrogen bond. If you do get a signal at 3100, that tells you that there is an sp2 hybridized carbon-hydrogen bond, and if you get a signal at 31, that tells you it's sp hybridized carbon-hydrogen. Okay, so then actually one more thing that's going to affect this, okay? So that's looking at carbon-hydrogen and what that can tell us, that region particularly of the spectrum. There is one other factor that's going to play a role in determining how we're going to interpret our IR spectrum and what wave number we're seeing absorbance at, okay? So let's imagine that we have a ketone, right? And we're looking in the double bond region of the IR spectrum, the diagnostic region, and we're seeing a signal for that ketone where we would expect it. And we compare that with the conjugated ketone, same exact bond that we're looking at, carbon-oxygen, so mass isn't going to affect anything, and we're seeing it at a little bit lower frequency, right? So a little bit lower frequency, a little bit lower energy. Why do you think this is? So for the first one, can we draw any resonance structures for this? There's one, right? So there's one where we have a difference in electronegativity here. So that oxygen is going to take all of the electrons. We're going to be left with a partial positive on the carbon, partial negative on the oxygen, okay? What about the guy on the right? Can we draw any resonance structures for that? So same thing we can start with. We'll give those electrons to that guy. We're going to be left with a negative here, a positive here, and a double bond here. Can I draw another resonance structure? Yes, right? So we can move these guys to here, and we would be left with something that looks like this, negative, and a positive, okay? Now, as we compare these two, this we know isn't going to contribute very much, right? But it is a molecule that has this bond depicted as a what? So specifically, because this is the bond that we're looking at, we have one resonance structure where this is not a double bond. What is it instead? A single bond, right? Who's stronger, double or single?
Double.
Double bond, right? So for this guy, it's like, okay, this is a partial contributor, but it's there, right? How many different resonance contributors do we have where we have that same bond for the conjugated ketone depicted as a single bond? Two, right? So because of that, right, because this guy has two resonance contributors where this is a much weaker bond, we're going to see absorbance for this guy, for this conjugated ketone, at a lower frequency, at a lower energy, because for two of the resonance contributors, it's not a double bond, it's a single bond, which is a weaker bond. Okay? So resonance is also going to play a role in determining the wave number of absorbance. Okay, so let's go ahead and try a problem that deals with this. So the first one, I've given you guys two molecules, and I want you to, with these specific highlighted bonds, I want you to order them in order of increasing wave number. So starting at the lowest wave number, moving to the highest wave number. So again, hopefully it's clear. A is this bond, B is this bond, and then C is this bond. And then down here I'm looking at A versus B. Or I can highlight them on here. Okay, so we went over this in class for two different molecules. So we've got molecule A, or maybe we'll call it molecule 1 because I use A's. So we'll call this molecule 1 and then molecule 2. We're going to rank the bonds that are highlighted in order of increasing wave number. So we're going to start with the lowest wave number, and again, wave number is represented by nu with a little, I think it's tilde on top, or a little hat on top, to highest wave number. So highest wave number, okay? All right, so remember, with respect to wave number, we model this as a spring, right? So we've got our wave number. We model this frequency, or the frequency at which we are going to absorb light, or the wave number at which we're going to absorb light. We model this as two masses on a spring, right? So we utilize kind of like a derivatized version of Hooke's law. Right? And Hooke's law depends on two different things. Number one, it depends on what we call the force constant. All right, so force constant in terms of our bond, that's like how springy or how tight that spring is, right? So the strong, we're looking at essentially a measure of bond strength here. And then this is also related to the mass of the two atoms that are on the spring, or the mass of the two things that are on the spring. So we call this reduced mass. Essentially, reduced mass is just a combination of the two masses, right? So what we find for our wave number is that we are directly proportional. So wave number is directly proportional to bond strength, and wave number is inversely proportional to reduced mass, okay? So because of that, what we're going to find is that single bonds are going to absorb at the lowest. So if we start down here at the lowest, single bonds are going to absorb at the lowest wave number. So lowest wave number, and then we're going to find double bonds at the second-ish, and then we're going to find triple bonds, right? But those are all going to be kind of usurped via anything attached to hydrogen, right? Because again, bond strength, big indicator, the frequency at which we're going to absorb light, but also that reduced mass. For hydrogen, because hydrogen is so light, reduced mass is going to be really small, so really tiny, and so the frequency at which we absorb light is going to be very large, okay? So essentially what we find is single bonds are about 400 to about 1500. We don't really care about those. Double bonds are about 1500 to about 1900 inverse centimeters. Triple bonds are about 19 to 23. And then for anything attached to hydrogen, so carbon attached to hydrogen, oxygen, nitrogen, etc., these are all going to be above about 27. So this is about 27 to 4,000, okay? Okay, so with that in mind, we can go ahead and try to start ordering these, right? So in the first molecule, we've got a carbon-carbon triple bond, we've got a carbon-carbon double bond, and then we've got a carbon-hydrogen bond. And most importantly, this carbon is sp2 hybridized, right? So that's going to kind of matter about which wave number we could expect to find a signal or absorbance at. All right, so then if we look at this guy, we do have a single bond here, but because it's carbon-hydrogen, it's actually going to be at the highest wave number. So C is going to be the highest. We have a triple bond, we have a double bond. So because the triple bond is stronger than the double bond, it's going to be the medium wave number. And then at the very lowest end, we'll have that double bond, right? So B is going to be less than A, is going to be less than C. Again, two different things that go into it, bond strength as well as if you have anything attached to hydrogen. Okay, so then in 2, so this guy is down here. Number 2, we have A and we have B. And A is, let me draw it on here, a carbon-carbon single bond, and B is a carbon-hydrogen single bond, okay? So again, single bonds are going to be the lowest, except for anything attached to hydrogen. So carbon-carbon is going to be our lowest wave number, so this guy will be our lowest in this molecule, and this guy, carbon-hydrogen, this is sp3 hybridized carbon-hydrogen, is going to be our highest. So A is going to be less than B. Okay? And again, here we'd expect this about 29 inverse centimeters. It's not going to be super indicative of 29 because there's going to be a bunch of those carbon-hydrogen bonds in that. Here, though, this is fairly unique. So for sp2 hybridized carbon hydrogens, we'd expect this at about 31 inverse centimeters. And that's kind of unique with respect to the molecule. Okay, so signal intensity. So what do I mean by signal intensity, right? So let's say that we have some sort of IR spectrum, and we look at it and we see, oh, well, for whatever this is, we get a very, very strong absorbance at whatever wave number this is, whereas for whatever this bond is, we get a very weak absorbance, right? We don't get as strong of a peak comparatively to what we would call a strong signal, right? This is what I mean by difference in intensity. For something that absorbs light really, really, really well, we get that and we indicate that by a large percent transmittance, or going very, very, very close to zero, as much as possible, whereas something that we would call a weak signal doesn't absorb as much, right? So we get a very, very shallow-ish peak, okay? Now, what's going to actually affect this? How are we going to utilize this intensity to figure out what type of bond that we're actually looking at, okay? All right, so I want to go back to our little model here of how we're imagining these bonds, right? And so again, we have two masses, and they are on this spring, okay? And let's say that we're looking at specifically a carbon-oxygen double bond, okay? All right, so when we imagine this vibration, right, we're imagining these two masses coming close together and coming far apart, close together, far apart, close together, okay? What else do you think you can tell me about this bond, this carbon-oxygen double bond, right? Is this a polar bond? Carbon-oxygen, is there a large difference in electronegativity? Yes, right? So oxygen's fairly electronegative. So we get a nice large charge separation where oxygen tends to take a lot of those electrons towards itself, leaving carbon with this nice partial positive charge, right? What do we call that? That separation of charge? Dipole moment, right? So we get a really strong dipole moment with respect to this bond because this bond is very polar, right? We get this large charge separation, okay? Now, as a reminder, dipole moments depend not only on the magnitude of the charge separation, but also on the distance between them, okay? So this guy, mu, is our dipole moment. It depends on the magnitude of charge separation, but it also depends on the distance between the two charges, okay? So as this bond vibrates, what happens to the distance between those two partial charges? It fluctuates, right? So we come really close together, we come really far apart. What's going to happen, therefore, to the dipole moment of this bond?
I'm assuming it's going to change.
Right, so it's also going to fluctuate. So it comes really close together, really far apart. What this is going to do, this movement of electric charge, is essentially is going to generate its own little electric field, okay? It's very similar to an antenna. What does an antenna do? It's essentially just oscillating little electric charges that generate its own little electric field, okay? Because of that, because it's generating its own little electric field, it's going to kind of serve as an antenna for other types of electric fields, other types of electromagnetic radiation, okay? So because it's generating its own little electric field, it's very, very, very good at absorbing electromagnetic radiation. So because of that, because we get this nice big oscillation of these charges, we're going to get a bond that's very, very, very good at absorbing electromagnetic radiation, and that's going to lead overall to a very strong signal because we're absorbing light really, really, really well, okay? Again, what did that depend on?
The dipole moment, or the difference in charges.
Difference in charges, right? So we had a very polar bond with respect to our carbon-oxygen bond that led to a large electric charge difference. When that thing vibrated, we got that nice little oscillating dipole, which generated our nice little antenna, okay? Yes?
So you're saying the more magnetic difference, charge difference, the better the waveform?
The stronger or the larger the overall polar bond, the larger the magnitude of that polar bond, the better that bond is going to be at absorbing electromagnetic radiation, so the more intense the signal you're going to get, the sharper the signal. Sharp's probably not the best word to use, but more intense signal, yes.
So if it was like a triple bond with like, I don't know, like it's like sulfur and a carbon, like that'd be like, would that give off a big, I guess, wave?
So hold on just 1 second. So yes, okay, so that's a nice polar bond, right?
Okay.
Makes a nice big electric field, very, very good antenna. We get a nice strong absorbance, right? What if we were comparing instead something like carbon, like something like this, right? An alkene, right? We have a carbon-carbon double bond, right? What's on the other side? What's on this carbon over here? It's not drawn, right? But what's implied there? We get 2 hydrogens, right? So here we have a carbon that's attached to 2 hydrogens versus a carbon that's attached to, what are these guys down here? These are methyl groups, right? So now, would you look at this bond, this specifically, let me highlight this carbon-carbon double bond, because that's what we're looking at. Would you say that's a polar bond? No, right? You wouldn't say it's a polar bond because it's carbon-carbon. It's usually fairly nonpolar. Is there still a slight difference in electronegativity, though?
Yeah.
Because this carbon is attached to a hydrogen, whereas this carbon is attached to a carbon. Yes, so even though this is nonpolar in our like canonical polarity idea, this is still slightly polar. Tiny, tiny, tiny little bit, so that we do get a partial negative up here and we do get a partial positive up here, right? That difference in charge, though, these little charges versus these charges, is much, much, much smaller, right? So again, when we see this bond vibrate, we still have the separation of charge. We do get this oscillating dipole, but its actual magnitude is much smaller comparatively, meaning it doesn't form a very good antenna and it's not very good at absorbing electromagnetic radiation, okay? So this type of bond would result in what we call a weak signal, because we don't get this nice large difference in charge, we don't get this nice oscillating dipole, we don't get this great antenna, so we're not that great at absorbing electromagnetic radiation. Okay? Now, there's an important little corollary to this that I'm going to note, and that's the fact that to actually absorb infrared radiation, you have to have a dipole moment. There has to be a slight charge separation. So for example, let's say that we were looking at something like this, where we had a carbon-carbon double bond, but now the groups on either side of that were exactly the same. And again, we're looking at this bond in particular, right? So now, for this guy, this is a symmetric alkene, right? We have the exact same thing. Oh, let me fix that. We have the exact same thing on both sides of that double bond. What type of bond is this?
Non-polar.
It's nonpolar, but more importantly, because this is symmetric, and this guy sees the exact same thing on this side as it does this side, is there any dipole moment created for this at all? No. So, do you expect to see a carbon-carbon double bond in the diagnostic region? You would, except it doesn't have a dipole. Because this doesn't have a dipole, there is no signal at all. You will not find this bond because there is no dipole moment.
No dipole moment, no signal?
No dipole moment, no signal. Because this is symmetric, there's no dipole, so there's no signal. Yes?
So on your wave number here, that flat line on top, that is your no signal, if there was, right?
Yeah, so how would that represent itself? It'd be up here.
Okay.
This would be no signal.
So it technically still be part of the diagnostic area, we just can't.
You can't see it. So the problem with that is there's a double bond in there. If it's a symmetric double bond, there's no dipole, then it's still there. There's still a double bond, but you're just not going to find it in the infrared spectrum. There's not going to be any indication that it's actually there. Okay. So anytime we have no dipole, because we have a symmetric molecule, dipole, we will have no signal. Okay, so weak, strong, what do we actually want to take away from this? So note that our one strong signal was our carbon-oxygen bond. What is this called again? There's like a lot of different, like we have ketones, we have aldehydes, but just overall, when we have a carbon-oxygen double bond, this is what I call a carbonyl. Carbonyl. Carbonyls show up really well in the IR spectrum, right? And so they have these nice, strong signals, you're going to have these beautiful peaks, and you should always expect them at about 1,700 inverse centimeters. Everything else is not going to be as nice and pretty and beautiful. So big takeaway here, You get a nice strong signal at about 1700. It is almost always going to be a carbon-oxygen double bond. Yes?
So my signal, as far as the intensity goes, is how deep it is?
How deep it is, how
Okay.
deep the trough goes, or how deep the peak goes.
So if I had multiple carbonyls, it would show up on the left side of the...
It would show up, so you're saying diagnostic region? Yeah, so it's going to be 1700. The beginning of the diagnostic is about 15.
Okay.
So it's going to be to the left of it, and it will be around 1680 to about 1750, depending on the things that are attached to it. Okay, so that's intensity, right? How strong a signal is versus how weak a signal is going to tell us mainly about the polarity of the bond we're looking at, the dipole moment that's created, okay? Stronger the dipole, stronger the signal. Okay, so the last characteristic that we're going to talk about is shape. Because when we look at these spectrums, we're going to find a couple of different types of shapes in our overall spectrum, okay? So now, one thing I want to do is I want to define what I mean by shape. So for some signals, we're going to find, or for the majority of signals, we're going to find it what we call a very narrow signal, meaning that the width of our peak here is very small. Right, so this width is fairly small. This is what we mean by a very narrow signal. The converse to that, or the other side of that, is what we call a broad signal. And a broad signal is not going to have this nice small width with respect to the peak. Instead, we're going to get this very wide distance, very wide peak overall. Right, so we're looking at something that's very small, very narrow signal, versus something that's very wide, a very broad signal. And the various things that are going to lead to whether or not something is broad versus narrow, what we can actually take away from this broad versus narrow signal, okay? Okay, so mainly, most things will be narrow. There's only a couple exceptions to the things that will actually produce a broad signal. And the first one we're going to talk about is what we'll find in something like ethanol. Okay, so in ethanol, let's say we're looking at the IR spectrum for ethanol. We've got this floating around, right? If we look at this molecule, and we're looking specifically in the diagnostic region, so we're cutting this off about 1500 and only looking to the left of this, what would we expect to find? We already know it's ethanol, right? We already know this is the molecule, this is the IR spectrum for it. What should we actually be looking for in the diagnostic region that's present in this molecule?
There's a dipole moment to a huge peak over 1700.
So thing with this, right, when we talk about double bonds, so double bonds end up being between about 15 to about 18. And we talked about where we could expect double bonds at, depending on the atoms, right? Triple bonds are a little bit higher. It's about 19 to about 23, right? So these guys would be triple bonds. Anything that was about 27 and above, who was that telling us about? It wasn't a double, it wasn't a triple. This is when the reduced mass came in. Anything to the left of 2700 was dealing with something attached to who? Hydrogen, right? Because hydrogen is the smallest little thing. That reduced mass is really tiny for that, so we see absorbance at a very high wave number for anything attached to a hydrogen, okay? So if we look at this molecule, are there any double bonds in this molecule? No, so we can't expect to see anything in this region. Are there any triple bonds in this molecule? No, right? So we can't expect to see anything here. The only thing that we're going to see for this molecule are carbon-hydrogen bonds, specifically sp3 hybridized. Remember, they are found in a particular region, and then oxygen-hydrogen, okay? And so we'll say, okay, we expect to find this bond at this very high wave number over here, right, to the left of 2700, and specifically for this oxygen-hydrogen, we expect to find this about 36 inverse centimeters, 3600, pardon me, inverse centimeters, okay? Okay, so that's one thing, okay? That's where we expect to find this bond, depending on the energy of it and its vibration. We do get a nice charge separation, right? Nice polar bond, so we have this nice dipole moment. Now, what else can this molecule do? And this is kind of the whole purpose behind what's going to make a broad signal versus a narrow signal. What else can this molecule participate in? If we draw in our partial charges here, so we've got our partial positive hydrogen, our partial negative oxygen, what else can this molecule participate in with another molecule just like it. Right, so let's say I drew another ethanol molecule over here, and this is our other ethanol. We've got our little partial positive here, or partial negative here. What can these guys do with respect to one another?
Come together, they can share the charges.
But which one? What is this called? So this hydrogen, which has partial positive, is very much attracted to these lone pairs of electrons on this oxygen, it's partial negative. What is this called specifically? What type of intermolecular force is this? Hydrogen attracted to this negative charge on the oxygen. This is hydrogen bonding, right? So this is how your DNA is held together. We have hydrogen bonding that takes place because we have a hydrogen that is attached to an oxygen, right? We can participate in these hydrogen bonding. So we do the same thing. This hydrogen is also very attracted to the lone pairs of electrons on this oxygen. We get these nice hydrogen bonds, okay? Now, if this guy is kind of going over here and kind of bonding with this oxygen, what do you think it's going to do to this bond that we're actually looking at with respect to our IR radiation, our infrared spectrum? You think this guy going over here and being attracted to this guy, you think it's going to strengthen this bond or weaken this bond? It's going to weaken it, right? So because of this hydrogen bonding, for this bond right here, we're actually going to see it weakened slightly, right? And so what is that going to do in terms of where we would expect to find this in the infrared spectrum? If we have a weaker bond, we're going to absorb light at a little bit tinier of a wave number, right? So this weakening, we're going to absorb at a little bit lower of a wave number, okay? Okay. So just the presence of that hydrogen bond is going to pull that peak a little bit to the right, right? But what we actually see in a solution of ethanol molecules is that we'll have some of these guys hydrogen bonding, right, weakening that bond. We'll have some of them not hydrogen bonding at all, so we'll get a very strong bond here, and we'll get it at 3600, which is where we expect it. We'll have some of them kind of in the middle, maybe hydrogen bonding a little bit, maybe not, right? So what's it going to do? We have some that are participating in this, pulling that peak down, some that are-ish, and some that aren't. What's that going to do overall to the width of our signal? Essentially, we're going to get this distribution of all of these guys contributing, and so what's that going to do overall to our signal? Instead of it being nice and sharp right on, it's going to broaden it, okay? So because these guys are this wide distribution of hydrogen bonds, we're going to get this wide distribution of frequencies, and that's what broadens our signal overall, okay? So because the alcohol group can hydrogen bond, that hydrogen bonding is going to result in a broadening of our signal, and so that's essentially why we would get a broad signal. So a big telltale signal in the infrared spectrum is a very, very, very broad signal that hovers about 35 to 3600 inverse centimeters, right? If you saw this up here, who do you know this is almost 100% due to?
The carbon still.
This guy specifically, O to an H. What is this called?
No, it's carbon.
Functional group. What is an OH called in a functional group? Alcohol, right? So if you look at an IR spectrum and you see this broad signal that is about 32 to 3600, it is an alcohol group.
Okay.
It is an alcohol, okay? So again, OH, if you see absorbance between a nice broad signal between 32 and 36 inverse centimeters, tells you it is an alcohol. There is an alcohol present in the molecule, okay? Okay, so there was another one that was thrown around in there. What is the difference between an alcohol and a carboxylic acid? What does a carboxylic acid look like as a functional group? So in a carboxylic acid, we have a carbon that has a double bond to oxygen, right? What else is this bound to? Say over on this side, it's like other alkyl chains, but what else does this have to be present for a carboxylic acid?
No.
Right, so carboxylic acid is a C double bound to an oxygen that is also bound to an OH, okay? So in a carboxylic acid, we see this exact same broadening, right? Because we still have a nice alcohol group on the end here, which is capable of hydrogen bonding. Now, the difference between carboxylic acids and alcohols, though, is that we can actually get more hydrogen bonding, because in just an alcohol, all we had was our partial negative on the oxygen, partial positive on the hydrogen. But for carboxylic acid, is there another region of partial negative charge?
The oxygen and carbon.
Right, so in carboxylic acids, we also have this other region by which the hydrogen can be attracted to a partial negative charge. So because of this, we get this gigantic distribution of hydrogen bonding between a hydrogen and this guy, and a hydrogen and this guy, and vice versa, okay? When we look at the spectrum for carboxylic acids compared to alcohols, how much broader is this comparatively to what we just expect for an alcohol by itself? This is the OH group for the carboxylic acid. How much broader is that compared to what we just saw for the alcohol?
A lot, bro.
Very much broader, okay? So for this guy, this ends up being about 2,200, too many zeros, 2,200 inverse centimeters, all the way to about 3,600. This gigantic broad signal in this region of the IR spectrum, this is almost always the alcohol group of a carboxylic acid, okay? So super broad like this, you know, oh, this is the alcohol group, this is the OH stretch of our carboxylic acid, okay? Now, for this carboxylic acid, what else could we expect to see in our IR spectrum? If this is the OH bond, this is this bond particularly, where else could we expect to see a peak? Because what else do we have the presence of? This guy, right? Where would we expect to see this carbonyl group?
Under the
So this bond particularly is a carbon-oxygen double bond, right? We would expect to see this at about 1,700 inverse centimeters. What type of signal? Would it be a very weak signal, a very strong signal? Very strong signal, right? And so for a carboxylic acid, you will get a very broad signal between 22 and 36. That's correlating to the OH bond of the carboxylic acid molecule, but you'll also get a very strong signal at about 1,700 inverse centimeters. That is particularly due to that carbonyl group in the carboxylic acid moiety, right? So again, it's like all of this evidence is telling us, oh, well, this is from a carbonyl. I know that's from a carbonyl. It's a strong signal about 1,700, and this is from the alcohol group of a carboxylic acid. Those two combined tells me that there's a carboxylic acid in the molecule. Okay, so then finally, one more group with respect to shape. So we talked about alcohol giving us a broad signal. We talked about how in carboxylic acids that's going to be even more pronounced. And then finally, the last little special one that we talk about is the amine group. So does anyone remember what an amine looks like?
It has nitrogen.
There's a nitrogen. So nitrogen, let's say that nitrogen on one side is attached to other alkyl groups, other carbons, whatever. What else does nitrogen have to be attached to, though? Has to be attached to a hydrogen, right? So when we're looking for amines, we're specifically looking for this bond, right? Again, it's nitrogen attached to a hydrogen. We're going to find that at about 34 to 3,500 inverse centimeters. Again, in that region of the hydrogen attached to things, okay? Now, depending on what else is attached to this nitrogen is going to depend on what we actually find there, okay? So there are two different types of amines. One of them is called a primary amine. So we call this a primary amine. And the other is called a secondary amine. And in the secondary amine, we're going to have an R to an R to an H. We'll go ahead and draw in our lone pairs. This is our secondary amine, and we can abbreviate that as a 1 with a, what is this called? A degree sign, and then a 2 with a degree sign, okay? How do these two differ? In a primary amine, that nitrogen is attached to how many other hydrogens?
They're both just one.
So primary amine, we have nitrogen attached to 2 hydrogens and 1 other alkyl group. In a secondary mean, we have nitrogen attached to how many hydrogens?
One.
One hydrogen and then two other alkyl groups, right? That's where the primary and the secondary come from, is how many other carbons is this nitrogen attached to. In primary, it's just one, right? And in secondary, it's two, right? That also depends on how many hydrogens are going to be there when we're looking at this group in the IR spectrum, okay? Now, depending on whether or not we have a primary or secondary mean, depends on how many actual signals we see for the nitrogen-hydrogen bond, okay? If we have a primary mean, where we have two hydrogens, what we're actually going to see is two separate peaks in our IR spectrum for that nitrogen-hydrogen bond, okay? You may think this is due to the two different bonds, right? It's actually not, though, right? In reality, what this is due to is the fact that these bonds stretch differently. So nitrogen-hydrogen can have symmetric stretching, where these guys are moving together like this, or they can have what's called asymmetric stretching, where one of them is moving in and out and in and out and in and out, okay? So somebody can symmetric stretch, or the other one can asymmetric stretch. That's why we get these two separate peaks. Okay. So for the primary means, we get two peaks. Again, they're about 34 to 3,500. For secondary means, though, when there's only one hydrogen, we don't get two peaks, we only get one. So one peak versus two is going to tell us whether or not we have a primary amine versus a secondary amine. Two peaks is from a primary amine, one peak is from a secondary amine. Okay, so that are all of the various characteristics in determining what type of functional group is present in a molecule looking at an IR spectrum. So now I'm going to kind of give you guys some pointers on how to analyze